Hello, everyone. Thank you for joining me. My name is Gopalakrishnan, and I am pleased to present to you my research on secondary electron generation from solar wind ion impacts on a solid surface. Next. So as we know, the moon has no global magnetic field or atmosphere, which means that it's directly influenced by the solar wind charging. So as you can see on the left, this solar wind charging creates a complex electrical environment near the surface, which also produces a lot of hazard for future lunar exploration. The main one of interest for us is dust charging and lofting. So as we know, when dust is charged, it can become lofted up into the atmosphere and it can have unpredictable motions. And so the main reason why we care about this is because the dust is extremely sharp, as you can see on the right. So it's almost like fiberglass, and this can cover the surface of astronaut suits or satellites, and it can make it very difficult to remove. And so this plasma charging environment is mainly driven by both solar wind ions and electrons, but also photoelectrons from UV radiation and secondary electrons. Next. So secondary electron emission is a process where a high energy particle impacts the surface and is able to transfer its energy, either by kinetic or potential energy transfer, into electrons within the material, eventually releasing them. So typically, whenever we consider secondary electron emission, we are usually talking about electron-generated secondary electron emission, which is extensively studied. However, we're more interested in ion-generated secondary electron emission, which is usually neglected because it's usually a lower density than photoelectrons or solar wind electrons. Next. So there's a couple scenarios of interest where ion-generated secondary electron emission may become really important. So the first of which I'll talk about is lava tubes. So as you can see on the left is an image of a lava tube skylight. Lava tubes are thought to be habitable, natural lunar habitats that might be able to shield the bottom surface and the tubes underneath the surface from the harsh plasma environment above. And so a numerical simulation originally showed that the solar wind electrons, to do their thermal motions, would be deposited onto the sidewalls, causing the bottom surface to become charged very positively, almost on the order of the ion energy. However, when we ran this in the laboratory, what we ended up finding was that ion impacts on the lava tube sidewalls caused secondary electrons to be diverted to the bottom surface, partially neutralizing that charge. Next. Another scenario of interest is permanently shadowed regions. So as many of you know, these are locations near the lunar poles that the UV radiation goes directly overhead. The thermal electrons are able to be diverted into the crater, and the ambipolar electric field diverts ions towards the crater. Because of the lack of photoelectrons and the solar wind electrons being diverted further into the crater, ion-generated secondary electrons might be important here. And so we've actually ran an experiment to make sure that dust mobilization from ions is possible. And what we found is that with lunar or Mars simulants, it is possible to mobilize dust from ion-generated secondary electrons. Next. And so in order to more experimentally verify the secondary electron yield from ions, we decided to run this experiment in the Colorado Solar Wind experiment, or the CSWE machine. So there's a very large ion beam device that allows us to put large experiments inside of there and run multiple tests. So essentially it works by inputting nitrogen or argon gas into an ion source where a hot cathode emits thermionic electrons and ionizes the gas. An anode and ion optics forms the ion beam, and a neutralizer on the outside releases 1 electron per ion it measures, keeping the plasma quasi-neutral. So this results in a supersonic ions and thermal electrons, which mimics the solar wind. Next. So in order to actually be able to measure the secondary electron yield, I use a retarding field energy analyzer, or REA. And so I use this in 2 different modes. So the REA consists of 4 grids and a collector, and I bias the grids to different potentials in order to select different charge populations. So in both of the modes that I'm showing here, the first grid, the 0th grid, is grounded to allow all the charge populations through. The first grid acts as the electron repelling grid, deflecting all the solar wind electrons away. The second grid acts as an ion selecting or ion filtering grid. So it's swept from a low bias voltage up to above the ion energy, and only ions above that bias voltage are able to pass through. The third grid is the secondary electron repelling grid. So again, to repel any secondary electrons that were generated at the grids before. And the collector just measures the resultant current. In the first mode I'm showing, the ion energy analyzer, or IEA mode, the collector is biased such that any secondary electrons generated at the collector surface are recollected and don't show up as any net current. Whereas in IEA-SE mode, or ion energy analyzer for secondary electrons mode, that collector is now biased such that any secondary electrons generated at the collector surface are now being able to be measured. And so on the right, I'm showing how the current collected at the collector varies as a function of that bias on the second grid, the ion filtering bias. And so the difference between these two modes shows the secondary electron current, and then we're able to normalize that to the amount of ion current to get the secondary electron yield. Next. And so here what I'm showing you is the secondary electron yield as a function of the ion energy for incident nitrogen particles. And next. So what you can see is throughout this entire range of energies between 50 and 1,000 EV, the ion-generated secondary electron yield is non-negligible, and it reaches a maximum value of about 0.4 for 1,000 EV ions. Next. And next. And so this is important, again, for the lava tube scenario or the permanent shadow region scenario that I was talking about earlier. Next. And so in order to extrapolate our results to something that's more like the solar wind, we decided to test the mass dependence of the incident ions and see how that influences the secondary electron yield. So we repeated the same process, but now with incident argon particles. They're heavier. Next. And what you can see is that there's about a 2 times decrease in the ion secondary electron yield compared to the nitrogen case. Next. And so what this implies is that lower incident mass particles will have a higher secondary electron yield. And this is important, next, because the solar wind is made up of hydrogen and helium ions, not nitrogen or argon. And so if we extrapolate our results back, this would imply a pretty large yield for incident hydrogen ions. Next. Another thing we want to look at is the surface cleanliness effect. So because of the ambient atmosphere and the vacuum pumping system, there may be some contaminants on the surface. So what we decided to do was we ion sputtered this collector surface for multiple hours with high energy ions to remove any contaminants and test how a clean surface would have a secondary electron yield. Next. And so what you can see is that there's about a 2 times decrease in the ion secondary electron yield for nitrogen. And next. There's only a smaller change for incident ion argon particles. So what this implies is that a contaminated surface would have a larger secondary electron yield, especially for the lower mass hydrogen ions. Next. And so the reason why this is important is because, The reason why this is important is because during a landing or takeoff from a planetary surface, the plume from the exhaust of a lander will contaminate the surface nearby. And so it's important to understand how that will affect the secondary electron yield and thus further dust mobilization. Next. And so throughout this project, you really saw that the secondary electron yield from incident ions is non-negligible, and it has a very strong dependence on both the incident particle mass dependence and the surface cleanliness dependence. And so these are both very important considerations for future simulations and work for dust mobilization on the lunar surface. Thank you.